explain to you about finite fields. So we write P for Z modulo Pz, where P is prime. And we have seen, last time that if F is a finite field, then the characteristic of F is P for prime number P. And in this case, for this prime number P, the number of elements in F is equal to P to the n for some n. So we know that if you have a finite field, its characteristic must be a prime number, and the number of elements must be the power of this prime. Okay, that we have seen. So now we want to see that indeed, the first thing we want to see is that indeed for every prime power P to the n, there exists a field with as many elements. Okay? So first we make some simple lemma. So let P be a prime number. So no, so for now P is always a prime number. Okay, so let F be a field of characteristic P. Then okay. So then the first statement is if I take and I write Q equal to P to the n, then I can write the polynomial x to the q minus x as q simple roots in its splitting field. Okay, and this is very simple because this is a polynomial of degree q. So if all the roots are simple, there will be precisely q roots. So we only have to see that it has no multiple roots. So proof. If we take the derivative, what is this? This is so if I order this would be q times x to the q minus 1 minus 1. But q is equal to 0. No, it's p to the n. Q is equal to 0 in our field. It's equal to minus 1, which is different from 0. So the derivative of this thing is the constant polynomial 1, minus 1. And so therefore the derivative has no 0. And the multiple root is always a common 0 of the polynomial and its derivative. So the polynomial can have no multiple roots. Now, okay, now we want to see the first result. As I said, we have seen that every finite field has to have p to the n elements for some prime number p and some number n. Now we want to see conversely that for every prime power p to the n, there is a field with p to the n elements. So now I say q is equal to n, so there is a field with q elements. Do you have an idea where this wonderful line was? Yeah, that's interesting. But anyway, let's just...
Move to the left. There's so much. Yeah.
Well, maybe can you make it straight? Okay. What?
That lemma is also true if we say Q a multiple of P.
Q is a power of P, yeah.
No, but let's suppose that Q is a multiple of P.
Yeah.
Is it true?
Well, there's no field, you know, if it's just a
No,
multiple.
just the particular.
Yeah. I mean, this statement would be, if there was a field with so many elements, then the statement would be true. But on the other hand, we have seen that it has to actually be a power of this. Because here it's just, if Q is a multiple of P, then the derivative will be 0. That's true. But, you know, on the other hand, we know that F will be a vector space over Fp, and therefore its number of elements is a power of P. No? I mean, we saw this last time. Okay. There's a field with elements, and so what we do? So we first look at the splitting field of this polynomial. Let K be the splitting field of this polynomial over Fp. And now, we will in a moment see that, we will later see that this actually is a field with Q elements. But for the moment we don't know that. Instead, we just take a subset of it, which later will turn out to be the whole thing. So let F be the set of all elements in K, which are solutions to this equation. So which are zeros of this polynomial. So this is a subset of K. So it's just the set of roots of F. So this polynomial. So what can we say about, obviously, F has Q elements. But we know that this thing has Q simple roots in its splitting field. So now I want to see that this is a field.
But we have assumption that characteristic of F should be P.
Yeah.
But
Yes.
how can we use this?
So we know that if the number of elements in the field is P to the n, the characteristic must be P.
Yeah, but we need to show that F is field. Yeah.
Yeah, we want to show that F is a field, yeah.
Of P power, order of F is P power m.
So I have said that, so I always write Q for P to the n. It's just a shorthand. We want to show that this F is a field with P to the n elements. It has Q elements, and now we want to show it's a field. But we have
now, if it is a field, then its characteristic will be P.
Well, no, I mean, this thing is already has characteristic P. Because, this is, K is the splitting field of x to the Q minus x over Fp. And Fp has characteristic P, and any extension has characteristic P. Okay. So F is a field. I mean, obviously we will have to use that the characteristic is P, otherwise this will also not be a field. I mean, you will not. No, if you are characteristic 0, you will never do something like that and claim that such a thing is a field. So let's see. So again, it's a field. So what does it mean? It should be, obviously, we have that it contains 1 is an element in F, and no, because if you take, and if A and B are elements in F, then first we can look at the product. So we want to show that A times B is in F. So if we take A, B to the Q, this is A to the Q times B to the Q, just because we're in a field. And A to the Q, now A lies in F, so A to the Q is equal to A, and this is equal to B. And so follows that A is in F. And if we take 1 over A, so maybe now A is non-zero, to the Q, by the way one operates in the field, this is 1 over A to the Q. A to the Q is equal to A, and this means it's also fine. So 1 over A is enough. This would, like this would hold in any field, but now we use characteristic P. If we take the sum to the Q, now we compute this by one computes this by the monomial theorem. So this is sum I from 0 to Q. Q choose I, A to the I, B to the Q minus I. But now we are, we know that it is well known that the binomial coefficient Q choose I is divisible by P unless I is equal to P or I is equal to 0. So for all, so we have Q choose I, so P divides Q choose I for I from 1 to Q minus 1. So that means the sum is just, there are only 2 summands, and if P divides it, we get 0 because in characteristic P. So only 2 summands survive. This is A to the Q plus B to the Q, and by our as we are in F, this is A plus B. Okay, and so we have seen that the axioms of a field are fulfilled. This is a field. Now I want to. So this is a field, and so we have therefore. So thus indeed, F is a field with 2 elements. Now I want to say a bit more. So we now know, that fields only exist with number of elements prime power, and for every prime power there exists a field. And now I want to say that for every prime power up to isomorphism there's a unique field. All fields with p to the n elements are isomorphic. And this is because they are the splitting fields of the self-same stupid polynomial. So proposition. Let F be a field with Q equal to p to the n elements, where again is a prime number, then F is a splitting field of the same polynomial x to q minus x. over Q over F. So first we want to see that every element of F has to satisfy this equation. So first, every A in F satisfies A to the Q minus A is equal to 0. Okay, so like there, so every element in the whole field satisfies this equation. So if A is equal to 0, this is obvious. No, 0 minus 0 is 0. And otherwise, if we take F without 0, with the multiplication, this is a group. Yeah. No? Is a group with Q minus 1 element. So we know that if we take an element of the group to the power, the order of the group, we get 1. So thus, for any A in F without 0, we have A to the Q minus 1 of, say, is equal to 1. And so we can multiply this by A. And so every element satisfies this equation. So now this polynomial x to the q minus x has degree q. So it can have at most q solutions in our field F. On the other hand, we know that this polynomial has no multiple roots, so it has precisely q roots in F. So let's say it again. X to the q minus x has at most q roots. Say in any extension of F, for instance in the splitting field, because it has degree Q. And as the roots are simple, as we have seen before, it has precisely Q roots in this extension. But on the other hand, we see already it has precisely Q zeros in F. So thus x to the q minus x splits over f into linear factors. So that means, so we know that f splits, that this polynomial splits into linear factors over f. So that means in particular that this, in this case, remember that if a polynomial splits over a field into linear factors, then if we just add all the roots in the bigger field to the smaller field, we get the splitting field. So, so that means thus the splitting field of x to the q minus x over q over q ft is in some sense ft, the roots of this polynomial. But these roots of the polynomial are precisely f itself, which is f. No? Because this thing just consists, f consists just of the roots, and it contains fp. So that's that. So thus this is a splitting. So together, if I just put together, we have the following classification. A finite field with p elements exists if and only if with n elements exists if and only if n is a prime power p to the n, q equal p to the n, and in this case, so, and furthermore, so this is the first, and the second, for any prime power q equal p to n, there exists up to isomorphism a unique field with p to the n elements, namely the splitting field of this polynomial. Okay, so
maybe it's Q not n.
what?
Q not n, a finite field with Q element exists if I don't.
Yeah. Well, okay. So I mean, here I wanted to say, so maybe m and if and only if. So because it's, you could think that there would be other numbers.
Because of the camera.
What?
Because of the camera.
What?
I mean, I understand, but just because of the camera, that's why I say.
Okay, so you want to for the rest of mankind. Okay, so okay, so that was that. So you see that finite fields are in some sense easy to understand. We have completely classified them, and that was not such a big effort. Now, obviously, we were mostly interested in fields which are not finite, and now we want to continue with our mainstream and study other field extensions. And so I said that we are trying to do Galois theory, and that is to try to understand field extensions in terms of some groups which are associated to the field extension, which are called the Galois groups. And so I want to introduce the Galois groups. So, and So we want to study the field extensions L over K in terms of the group. Of K automorphisms of L. And this will be called the Algebra. So let me just write it down. So let L over K the field extension so the Algebra group so which I denote Algebra of L over K of L over K is, as I said, is the group of K automorphisms of L. So this is a K automorphism, as you remember, is an automorphism, so an isomorphism from L to itself, which is the identity on K. And obviously these form a group under composition. Clearly, this is a group under composition. Now, you might be a little bit disappointed in some sense, because I told you we want to understand field extensions in terms of a group, and one could somehow have thought that there would be some very simple group associated with the field extension. And now if one looks at the definition, it looks quite terrible. How are you have this field extension, which you try to understand, and want to describe in terms of something which in some sense looks more difficult. No? If you don't understand the field extension, how do you understand the K automorphisms of L? Okay. So that's a reasonable question, but you will find out that actually one can make this reasonably concrete. So you will find out that in many cases, the scalar group can be viewed as some group of permutations of some roots of some polynomial. Okay, so that's much more explicit. And at any rate, it turns out one can use this. I mean, part of it is, in general, this can be incredibly complicated. But that's just, a fact of life. Some problems are very difficult. You can be formulated into something else which makes it easier, but it can still be very difficult. And so in general, this will be the case here, but many problems can be solved using this. And first, so we can start with a simple example. For instance, what is so the complex conjugation tau from C to C, which sends A plus IB to A minus IB, is an element of the variable of say C over R. Obviously the identity is always in it, but okay. So it's just something that follows from the definition. If you add these things or multiply these things, this will be compatible with it. This is a homomorphism. compatible with addition and multiplication. In fact, okay. Now we want to understand describe the Galois group in one simple case, namely the case of a simple algebraic extension. So at least we maybe don't give a complete answer in this case, but we can say a lot about it. So Galois group for a simple algebraic extension. K over K. So what is the statement? So first I recall something that we were using before in the group theory. So this is just this notation. So if for a finite set M, it doesn't have to be finite, but as before, we had defined S of M to be the set of all permutations of the elements in M. So all sigma from M to M bijective maps with the composition as a product. So this is the group of permutations of M. We had this when we were talking about it. And then we know that this S of M is equal to S M. So the symmetric group in as many, permuting the numbers 1 to M. So it's isomorphic to this S group. Okay, I just want to recall this. And I also recall what it means for an action to be simply transitive. So recall an action of a group G on a set. What was a set called? Whatever. M is called simply transitive if for all elements M1, M2 in M, there is a unique element G in G which stands M1 to M2. Okay, and we know that in this case at least if I assume that M is non-empty, we have that the number of elements in M is equal to the number of elements in G. Okay, so this we all had. And so let's, now we can formulate what happens here. So theorem. So let Ka of K be a simple algebraic extension. So let F be the minimal polynomial of A over K, and we look at the roots of this minimal polynomial in Ka. k such that f of b is equal to 0. So this is, you know, the set of roots of f in Ka. Then the Galois group of Ka over K acts simply transitively on this set R of these roots, and therefore, as we shall see, the Galois group of Ka is isomorphic to a subgroup of the set of permutations of R and the order of this group, so order, what is the order? And so maybe and the order of the Galois group of Ka over K is equal to R, which is smaller or equal to the degree of this minimum polynomial. Okay, so this is the statement. So it's not completely explicit, but we see that somehow the Galois group, an element in the Galois group, is determined by what it does to the roots of this minimal polynomial, and the action of the Galois group is simply transitive. So for any two elements in R, there's precisely one element in the Galois group which sets one to the other. Okay, so let's try to prove this. And again, you can see this is somehow one of the reasons why we like simple algebraic extensions, because in this case we can say a lot about the Galois group. And then, because of this, we'll also like the theorem of the primitive element, because it says all finite separable extensions are simple, so in some sense they can always be described in this way, although that's a bit unexplicit. So, what do we want to do? So let's take an element in the Galois group. So we have to see that an element in the Galois group will send roots of this minimal polynomial to other roots of the minimal polynomial, and that is determined by what it does to these roots. So first let's take any polynomial with coefficients in the smaller field. And we take an element B in Ka. Then we want to see what the Galois group does to the how it behaves if we put something into G and then apply it in the Galois group. So let's see. So if we take phi of G of D, so G was to some I equal 0 to n, where some, I haven't used n yet, ai x to the I. So this will be some I equal 0 to n, ai, so phi of ai b to the I, which is equal to some I equal 0 to n ai phi of b to the I, because this is a K homomorphism, so it's the identity on the elements of A, and it's a homomorphism, and so this is G of phi of A. Okay? So that means we can kind of pull phi in and out of the polynomial. So in particular, if G of phi was equal to 0, then G of phi of p is also 0. So in particular, if we now apply this to our minimal polynomial f, you see that it sends the zeros to the zeros. So thus, if p now is a 0 of f in K, then we have that 0 is equal, f of p obviously is equal to p of f of p, because p of 0 is 0, is equal to, and this was an f, to f of phi of p. So that means phi sends zeros of f to zeros of f. Thus, phi maps R, so the set of zeros of this thing, to itself. So, as phi is an automorphism of fields. So it's in particular injective. It's also, so as phi is injective, we also have that phi restricted to R, from R to R, is injective. And as R is a finite set, an injective map from a set to itself is a bijection. So thus biject. So that means if I take phi restricted to R, this is an element in the symmetric group of R. And it's clear that, so in the Galois group, the multiplication in the group is composition. And here, in the symmetric group, the multiplication on the group is composition. So the map, which sends phi to phi restricted to R, is a homomorphism. From the Galois group of Ka over K to S of R, which sends phi to phi restricted to R, is a group homomorphism. Okay, so we have okay. Now I want to see that this acts simply transitively on R. So we have seen this was the extension of three isomorphisms to simple algebraic extensions. That the following, for any two zeros of the minimal polynomial, so B1, B2 in R, there exists a unique K homomorphism phi from so KA what? Yeah, well, in principle, okay. Let me try to see. Yeah, now let me see. Well, anyway, first you're right, E1 to K of T2, which is so it's K homomorphism. Okay. Now, yeah, but you see, so let's say D is the degree of this polynomial, then F is the minimal polynomial of A over K. That means this polynomial which has a 0 also of B1 over K and of B2 over K. No, because it's irreducible as a 0. And so therefore it follows that the degree of K B1 over K is equal to the degree of K B2 over K is equal to the one of Ka over K, which is D, this degree. But we have assumed that B1 and B2 are both elements in Ka. So that means KB1 over K has the same degree as Ka over K, but it's contained in it. So they must be equal. So it follows KB1 is equal to KB2. Okay, I haven't, and so therefore, this element phi is an element in the, so the K isomorphisms from here to here are the same as elements in the Galois group. So it follows that for all E1, E2 in R, there exists a unique in the Galois group of Ka over K, such that P of P1 is equal to P2, which means it acts simply transitive. The Galois group of Ka over K acts simply transitively on R. Okay, so if the Galois group acts simply transitively on R, this means there's only one element in the Galois group which sends any given element B to itself, namely the identity, because there's always, for any pair of two elements, there's a unique map. So therefore there's only one element which sends an element to itself. So that means that the map from the Galois group to these permutations here is injective. So it follows that the map restriction to R from the Galois group of L, Ka over K to S of R is injective. So therefore the Galois group is isomorphic to its image, which is a subgroup. restricting to R a subgroup of S of R. And as the action is simply transitive, it follows that the number of elements in the Galois group is equal to the number of elements in R. And obviously, so these are the zeros of this minimal polynomial. So the number of zeros in Ka can be at most equal to the degree of the polynomial. Okay, so this was all that was claimed. Okay. So let's look at some very simple examples to see that different things can happen. So note, just see example. So if I take, well, for instance, the Galois group of, say, q square root of 2 over q, I claim this consists of the identity and the map which sends A plus B square root of 2 with A and B and Q to A minus B square root of 2. So you can so this is, in this case, we have a simple algebraic extension, so we know that, and this polynomial splits, so they are A over q square root of 2, the roots are square root of 2 and minus square root of 2, and there exists only two elements in the Galois group. One sends square root of 2 to itself, and then it must be the identity. The other one sends square root of 2 to minus square root of 2, and then, if you make this group homomorphism, it will do this. A field homomorphism will do this. So we know that the minimal polynomial of this field is x squared minus 2, which has degree 2. So we know therefore that the number of elements in the Galois group is 2, and we have seen these two elements. By the way, if we look at the Galois group of C over R, then by what we have seen, this will just be the identity and complex conjugation. Because this again is simple algebraic extension, the minimal polynomial. So C is equal to R I, and the minimal polynomial of I is x squared plus 1 of degree 2. So we know there are two elements. We have already seen two elements, namely the identity and complex conjugation, so this must be the thing. And anyway, it follows also directly from the definition. So here we see two examples where the Galois group has as many elements as it can have, the same as the degree of the minimal polynomial. So you see, I should maybe say, Yeah, I should have stressed this before. So here I said always, so in the theorem I said I take the degree of the minimal polynomial. But the degree of the minimal polynomial, so that the number of elements in R is at most the degree of the minimal polynomial of the field, of this A. But the degree of the minimal polynomial is also the degree of the field extension. So you could also say the number of elements in the Galois group is at most the degree of the field extension. In this case, the degree of the field extension is 2 and the number of elements in the Galois group is 2. So that's fine. But let's look at another example. Let's look at the Galois group of Q, the third root of 2 over Q. So what do we have here? I claim this consists only of the identity. So the degree of the field extension is 3, but the Galois group contains only one element. And why is that? So the minimal polynomial of third root of 2 over Q is, what is it? X to the third minus 2. So we know that's irreducible, and it's therefore the minimal polynomial. And its only root in Q, third root of 2, is third root of 2. No? Because we know if we, in the complex numbers, the other two roots are really complex, they are not real. And so, as this is these are real numbers, it follows that the only root of this polynomial in this field is this. And we know that. Sorry. Yeah, you can certainly come in. Yeah. I'm sorry you couldn't get out.
Yeah. I was in the first, so it seemed to me illogical to stand up in front of him.
No, in the end, people don't mind as much as we think. It's just this one moment, and then you're gone, and nobody remembers you. So that's good. Anyway, so and so, therefore, the Galois group acts simply transitive on the roots. There's only one root, so there's only one element in the Galois group, and obviously this must be the identity.
Please, I don't understand.
What didn't you understand?
Why the Galois group of this field extension is only the identity?
But this was supposed to be the explanation. So let me try again. So for this field extension, the minimal polynomial of this third root of 2 over Q is this one. And you can see this has only 1 0 in Q third root of 2. Because all the elements in Q third root of 2 are real numbers. And if you find the other two zeros of this polynomial will be genuinely complex. So we have only one root. Now our theorem said is that the Galois groups act simply transitively on the roots of this polynomial. But as we have only one root, the only group which can act simply transitively on one root is the group consisting of the identity. Okay.
If you take a complex number as an extension, it becomes something more.
What?
We can extension as a complex numbers instead of this.
Oh, I mean, what do you mean? If you take any other,
Instead of we take complex numbers, set of complex numbers.
We take the complex numbers, yes, and then
in this case, I think the group has three groups, three elements.
well, but basically, whenever we only take one, so obviously we can make a larger extension. We can take all the roots.
Yeah.
Okay, so this would be. So we take a bigger extension. So this would be Q third root of 2 and say e to the 2 pi I divided by 3, third root of 2. And that's actually enough. With this you have all the roots. So in this thing we have this polynomial will have 3 zeros. This is actually the splitting field of this polynomial. And we have the 3 zeros, third root of 2, e to the 2 pi I divided by 3, third root of 2, and e to the 4 pi I divided by 3, third root of 2 are the 3 roots. And in this case, the Galois group of this extension will actually permute them in an arbitrary way. So the Galois group will have 6 elements. And I will explain that later, but we will see in a moment that this Galois group has to have 6 elements, not just 3. Because you cannot just permute them cyclically, you can permute them in an arbitrary way.
But it must be less than degree.
No, because this is not a simple algebraic extension. And if you take any other root, and just the other root, it will still have only one root in that field, and the Galois group will be trivial. So, but anyway, for this thing, the degree is 6, but this is not a simple it is also a simple extension in some complicated way, but not a simple extension with this degree. The degree of the field extension will be 6. And we will see this. But in fact, now I will come to this. Now, in Galois theory, one studies, as I said, so-called Galois extensions, which are finite, separable, and normal extensions. Okay? So, definition. The field extension L over K is called a Galois extension if it is finite, separable. I can write better. And normal. And recall that if the characteristic of the field is 0, then separable is automatic. No? And we only need normal. And now we want to make a corollary, which is related also to your question. So let L over K be a Galois extension of degree n. The degree means the degree of L over K. So dimension of L is a K vector space. Then the Galois group of L over K is isomorphic to the subgroup of the symmetric group in n letters. This is n, which act simply transitively on the numbers 1 to n. So it's isomorphic to a subgroup of Sn, which acts simply transitively on the letters 1 to n. And in particular, the number of elements in the Galois group of L over K is equal to n. That means to the degree of the field extension. Okay. So for a Galois extension, the degree of the field extension is equal to the number of elements in the Galois group. So we see, for instance, in particular, it follows from this that this one is not a Galois extension. I mean, it's also kind of obvious, but that's not, because it's not. So the point is, now, we have just proven some similar result for simple algebraic extensions, and then obviously we use the theorem of the privative element, which tells us that if the field extension is separable, then then we can apply this result. And the fact that it's not, anyway, that's me go a little bit. So by the proof, we apply the theorem of the primitive element. We can write L or field L as K of A for some element A in K, in L. Okay. As L over K is normal, the minimal polynomial the f of A over K splits in L into linear factors. Now we know that in a normal extension, if you have an irreducible polynomial with coefficient in the smaller field, which has a zero in the bigger field, then it splits into linear factors. So in particular, this applies to the minimal polynomial. And as L over K is separable, F has no multiple roots in this. No multiple roots. So that means F has precisely as many zeros, the set of zeros of F, of this minimal polynomial, it has precisely n elements. So the number of elements of this is n. And now we can apply the previous theorem, which said that if we have a simple algebraic extension, then we have that the Galois group acts simply transitively of the roots of the minimal polynomial, and and this is precisely what we have here. Okay. So, do I have the time for this? Yeah, should be possible. So now, so this has precisely and distinct groups. So now we want to prove, so we still need to, so we have at least understood something about these Galois groups. So for Galois extensions, the number of elements in the Galois group is precisely equal to the number of elements in the group. And now we want to, so in some sense we will always want to understand the Galois group for Galois extensions. Now, so it's important for us also to know what the Galois group can precisely do. So what elements can be mapped. So what elements in the bigger field can be mapped to other elements. And for this, therefore, the following is a very useful proposition. Or whatever, a very useful result, which we will use. So very useful is the following. We need to understand the Galois group. So the following proposition. So we take again a Galois extension. And let's take two elements in the bigger field. And we ask ourselves, when is there an element in the Galois group which sends one to the other? Okay? And the statement is very simple. So there exists an element phi in the Galois group of L over K with, which sends one to the other, so with phi of A is equal to B if and only if A and B have the same minimal polynomial over K. So we have at least some criterion that we had seen before, that, you know, if, well, and so we have some criterion for being able to move one point to the other, namely they should have the same minimum power. So let's see. So it's an if and only if. So now assume they have the same minimal polynomial. So let A and B, the elements in L, with the same minimal polynomial over K. Which I don't want to use a name, but maybe F over K. So we know that in this case, if two polynomials have the same minimal polynomial, there will be, we have this extension of field homomorphism to simple algebraic extension. So then there exists a unique K homomorphism, say psi from Ka to Kb with phi of A is equal to B. This was with this extension to And now, so now we want to extend this. Now it's clear that we can extend this thing to an element in the Galois group of L over K, because L is both the splitting field of something over Ka and something over Kb. So let me just say. So L is so L over K is the Galois extension. So in particular, normal extension. Thus, L is the splitting field of, by our result is the splitting field of some polynomial with coefficients in K. Of some, say, G in Kx over K. But A and B are in L, so Ka and Kb are intermediate fields. Then we know that therefore L is also the splitting field of that same polynomial over Ka and over Kb. Is the splitting field of G over Ka and over Kb. So therefore, by the extension, by the result about extension to splitting fields, there's a unique extension of this psi to a homomorphism from L to L. So no, not the unique. There is it. It's not unique. Sorry. That was the extension to splitting field has no uniqueness, but there is an extension. By extension to splitting fields, there exists a map, say phi, which will turn out to be our phi, from L to L, with phi restricted to, say, Ka, is equal to psi from Ka to Kb, and thus P restricted to K is obviously then the identity on K, because this psi was already a K isomorphism, and P of A. So that means phi is an element in the Galois group of L over K, and P of A is equal to B. Okay, so this is one direction. If they have the same minimal polynomial, then one can send one to the other. And now for the converse. So let's now assume that A and B is in L and phi of A is equal to B for some element in the Galois group of L over K. And we want to have to show that they have the same minimal polynomial. So we look at the two minimal polynomials. So I don't know whether did I already give any name. Anyway, so here it's f, but now we are in a different, so I can give whatever name I want. So let f be the minimal polynomial of A over K, and G be the minimal polynomial of B over K. You have to show that they're equal. Now we use the same trick we used a moment ago. I mean, not so much a moment, maybe an hour ago. Namely, we have 0 is equal to f of A is equal to phi of f of A is equal to f of phi of A. No, the same thing, because f was a polynomial with coefficients in k, so the same trick as before works. So thus, which is f of b. So b is also a 0 of f. But f is the minimal polynomial of A. No, let me get it. So b is also 0 of f, but g is the minimal polynomial of this. Is the minimal polynomial of b over k. It follows that g divides f. In the same way, obviously we can exchange the roles for A and B. In the same way, f divides g. So they're equal because they're monic polynomials. Okay, so this comes kind of nice. Okay. Where am I? So, I mean, I will maybe not prove the next thing. I will just state. So we'll see that this is actually a quite powerful result. In particular, we will prove as a first thing next time the following result, which will actually be half of what is called the fundamental theorem of Galois theorem. And this is the following theorem. So we take a Galois extension and now we are interested in the sets of all elements in L which are fixed by all elements in the Galois group of L over K. So I could call this fix of Galois group of L over K to be the set of all A in L such that phi of A is equal to A for all phi in the Galois group of L over K. So, and then the answer is that the only way how this can happen is that an element can only be fixed by the whole of the Galois group if it already lies in K. Okay. So an element is fixed by all elements in the Galois group if and only if it lies in K. Yeah, well, I might have as I started a bit late, maybe I will finally do it. It's actually not so difficult now. It's mostly application of this result. So proof. Obviously, so we say that these two sets are equal. So that this thing is equal, that this fix is equal to this. So, so this inclusion, so that the elements of K lie in this fixed point locus is trivial. Because by definition, the elements in the Galois group are all the K homomorphisms of L. So all the phi which send every element of K to itself. And so by definition, this inclusion is true. So what we have to see is the other inclusion. So, well, we assume we are in the set. We have an element A is an element in L with phi of A is equal to A for all elements P in the Galois. Now, we somehow have to use the story with the minimal polynomial. We will want to show, we want to use the previous result to show that the minimal polynomial of A over L is x minus A, which means of A over K is x minus A. That's our A. So let F be the minimal polynomial of A over K. So as L over K is normal, we know that this F splits over K. F splits over L into linear factors. So assume we have another root, that P be in L, be another root of F. Then, by the previous result, we have there exists an element in the Galois group which sends A to B. There exists an element phi in the Galois group of L over K with phi of A is equal to B. So by our assumption, it follows, phi of A is A, you get that phi of A is A, so we have that A is equal to B. So that means thus all the roots of F are the same. But we also have assumed we have a Galois extension, so it's separable. So as L over K is Galois, and F is irreducible, so it's an irreducible element in Kx with a 0 in L. It follows it has no multiple roots in its splitting field, so it has no multiple roots. So F has no multiple roots. So we have a monic polynomial which has only one root and no multiple roots. And so it's just x minus a. A is an element in Q. Okay, so this is, you can see that we have this relatively simple argument which uses this thing. So this shows that this is rather powerful. Okay, so maybe I will stop here.